let's continue on power series. So here's the next theorem. Theorem convergence of power series. So for a power series, and I put it right here just to remind us what a power series looks like, centered at C, so it's this case, one of the following is true. Converges only at C, which means basically you put in C here and you get 0. So that's not a very interesting convergence, but it's true. Second, there exists an R greater than 0 such that the series is absolutely convergent for absolute value of x minus c less than r. So basically this difference is less than a certain value and diverges if greater than r. At r, that's where you have to test endpoints, and we'll talk about that. Or 3, the series is convergent absolutely for all x in r. So meaning every x it converges. So that you'll have one of those 3 things for series convergence. So let's look at this example. Find the interval of convergence of the series. And I just wrote some things here to show you that we use u sub n for the whole thing, and because we still consider this to be your a sub n. So that's the only reason we do that. All right, so let's go through this. So first, then, let's let u sub n be x to the n over the square root of n. Right, that's that whole thing. And then we do the ratio test again. All right, so then we look at the limit, and we look at absolute convergence. So it's the absolute value of u sub n plus 1 over u sub n as n approaches infinity. And we substitute and simplify all of that. So that's equal to the limit as n approaches infinity of the absolute value. And this is something you may want to stop and work on it yourself for a little bit. I'll go through this one. You're just going to be substituting in n plus 1 to the whole thing and see what happens. So it's x to the n plus 1 over the square root of n plus 1. Then it's root n over x to the n. Okay, then you simplify that, simplify all of this. So these will reduce, Okay, so it's the limit as n approaches infinity, absolute value. And so you have, there's no way to get rid of the roots. So you have root n over root n plus 1. That's not going to change. But your x is just going to be x, which is times x. And you can rewrite that as the limit root n over x, oops, not x, sorry, over n plus 1 as n approaches infinity of the absolute value of x. So that step, you can take out the absolute values of the root because that's positive anyway, can't be negative, and you're approaching large values. So that has to be less than 1. Well, you take this limit, right? So the next step is to go ahead and take this limit. You can bring the limit inside the radical, and then you're just looking at this basically rational function, although it's, integers. So you just get 1. So this whole thing goes to 1 as you approach infinity. And so it's just dependent on that absolute value. So we get equal to 1 times absolute value of x, absolute value of x less than 1. All right, so this implies the series is absolutely convergent, provided absolute value of x is less than 1. So you just have to test endpoints. So right now you have the radius of convergence is 1. So just to clarify a couple things. So the series is absolutely convergent if x is between 1 and -1, which is this statement above. I mean, that's the same thing. And you just want to say why by the ratio test. All right, so now we want to test endpoints. This is often what many forget to do, so don't forget to do it. So x equal to 1. We're looking at this sum of 1 over root n. All right, so what type of series is that? So I'm just putting in 1 for x. Ponder that for a second. So that is a divergent p-series. P equal to a half less than 1. All right, so then if x is -1, what's going to happen? You have the sum -1 to the n, 1 over root n. And we looked at that one before. What's going to happen there? That is a convergent alternating series. Okay, so that's, I mean, you wouldn't have to prove that one. You'd have to just say it. Earlier, before you do this, you'd have to show that's decreasing and alternating and all that. All right, so then you have the interval of convergence. So you say interval of convergence is, so you include the -1, but not the 1. So that's the interval of convergence, and the radius of convergence usually indicate that with an R. R is 1. So the radius of convergence is 1. So that's kind of going back to that theorem. Okay. Let's do the next one. So try this one. So we'll go on. So this one, I'll write it up and then try it, and then I'll just have the write up, and then we'll go on to the next theorem, which is differentiation and integration of power series and what they look like and when they converge. And we'll just look at a couple examples of that before we go on to Taylor series and Maclaurin series and all that. All right, so this last example, find the interval of convergence of, sometimes they give it to you in this form, and then you got to figure out a sub n and all. 1 minus 1/2 x minus 3 plus 1/3 x minus 3 squared plus -1 to the n, 1 over n plus 1 x minus 3 to the n plus . Okay, Okay, so that's what's given. And so first you'll need to figure out, well, no, it's right there. I mean, you don't have to figure it out. This is actually what the U sub n will be, right? So that's U sub n. Okay, so that's kind of nice that they gave that to you. And then use the ratio test. So pretty much all these that I've seen so far are the ratio test. And that's essentially our